recording.
So it's a great pleasure to introduce Nikita Kalin, who is going to continue his series of lectures about summations on topographs.
Yeah, thank you very much for the possibility to talk here. So today I'm gonna relate the results from the last time to quadratic forms. And that are quite recent results. Okay, not mine results, but somehow we rediscovered some of them. So first of all, let me remind, so what was the topic of the discussion for the last time? So we had the set A, the set of vectors in the first quadrant. That's the lattice vectors, such that the area of the parallelogram spanned by them is 1. So that's X, that's Y. And then, given this set of pairs of vectors, we can organize a summation. We just divide 1 by the length of x squared times length of y squared times length of the diagonal. Okay, square. And then take a sum, multiply by 4, and that's a pi. And last time we had 2 proofs of this formula. So one was via telescoping. So we just presented this sum as a certain, like, we presented each term as a sum of 3 terms, such that when we sum all of them, they cancel, like most of them cancel, and then, like, by some asymptotic consideration, we found that it's proportional to the angle here. That was one proof. And the second proof was even more geometric. That was about just areas of triangles. So remember that if we parameterize the points on half a circle by the lattice vectors, then actually this number is just the area of the corresponding triangle. And then the sum of the areas of such triangle, just pi over 2. And so up to constant, that's exactly what we have here. So 2 geometric proofs. But actually, this formula was discovered by Hurwitz more than 100 years ago. And the formula of Hurwitz is as follows. So let's look at it. So I will explain all the terms, maybe not now, but a bit later. Okay, so first of all, we have a constant. This constant omega d basically is almost always true. So if certain number d, the d is a negative number, integer, and if d is less than -4, that is 2. If d is -4 is 4, and if d is -3, it's 6. Okay, that's omega. Now, so we have a summation. Summation of what? Of all such triples of numbers, a, b, c, such that a is bigger than 0, b squared minus 4 is d. So that reminds us the discriminant of a quadratic equation, and indeed the discriminant. And we take a summation of a times c times a plus b plus c. So usually that's the infinite sum. Well, we can ask what is the value of the sum, how it's connected to other stuff. But anyway, the theorem of Hurwitz is that if you multiply this sum by the d power 3 over 2 and divide by 12 pi, then you have this constant 1 over omega d times h of d, where h of d is a very important number. That's called a class number for quadratic fields, but we will define it as the number of equivalence classes of binary quadratic forms with discriminant d less than 0. So on the next slide, I will explain what is that. So for now, it's just some formula for quite important number. And maybe you have seen some formulas for h of d, and usually these formulas are not that good in some senses. But there are a lot of classical formulas for h of d. But this formula is better somehow. And it was completely neglected. So this article of Hurwitz was never cited for 100 years. Because actually, no, he also wrote a lot of other stuff, and so this simple formula was kind of obscured. Okay, that's the formula. Now let me define the things. So that's the topic of today's lecture, is just to connect these two things. Okay, so now, so this talk is based on the following papers. Well, this should be one. So the first paper, that's the Hurwitz paper. It's 1905. And that's about binary quadratic forms and about the class number. And then there are two recent papers. The paper of Duke, Imoglu, Toth on the class number formula of Hurwitz. Basically, maybe they just found that article, maybe they rediscovered, I don't know. But anyway, they found, so they put it in a new modern language. And it's all very short and very nice paper. So I recommend to read it. And even better, there is even a more recent paper of Cornack Sullivan that's about the connection to topographs. And so this paper is very nicely written. I recommend to read it. And actually, there is a talk of Cormac on YouTube. So if you just put in YouTube search this Cornack Sullivan Scooney topographs and some infinite series, you will find that it's like 1 hour talk, and he will explain a lot of stuff about topographs and about his formulas. And well, and my today talk is based on these three articles. So I will not speak about my results. I will just try to connect, these formulas. Okay, now let's go to the definition of class number. So let's suppose that we have binary quadratic forms with integer coefficients. So always today, I suppose that A, B, and C are integers. Okay, so we have a binary quadratic form. Usually it's denoted by Q, for example. And when I write ABC, it means that that's a form ax squared plus bxy plus cy squared. Green. Red. Okay. Doesn't matter. Okay. And if we have two such forms, we may ask many questions. So for example, we may ask, okay, what are the values of these forms? For example, which numbers can be presented as a sum of two squares? So that's a basic question. For example, if you have a prime number and you ask when, well, a prime number P can be presented as a sum of two squares, right? Or maybe you can ask a question when a prime number P can be presented as a sum of x squared plus ny squared. Right, so basically the whole theory of binary quadratic forms stemmed from these two questions. Well, from this question. So which prime numbers can be presented in such a form? That is a question of Fermat, actually. And then Euler, he worked a lot about this topic. And actually that's how Euler discovered the quadratic reciprocity law, by considering many examples like that. So that's a basic question. So if you have a quadratic form with integer coefficients, which numbers can be presented as values of this form when you put x and y integers, right? So also always here we have integer numbers. And then there is a very natural notion of equivalence because we care about values of quadratic form on a lattice Z2. So we can twist the form by the automorphisms of the lattice. Or, for example, we can twist by the automorphisms which preserve orientation. So we say that two forms are equivalent. So the form ABC and A prime, B prime, C prime. If there exists a cell to Z transformation, so that's four integer numbers, alpha, beta, gamma, delta. Alpha, delta minus beta, gamma is 1, such that the form ax squared plus bxy plus cy squared is just the form given by alpha a prime, b prime, c prime, where you change the coordinates according to this SL to Z transformation. Okay, so this alpha, beta, gamma, delta gives you a 2 by 2 matrix with determinant 1. So it means that its matrix sends you Z2 to Z2. That's isomorphism, right? And then naturally, the values of the forms ABC and A prime, B prime, C prime, they're the same. So it's very natural equivalence relation. Actually, you can ask, okay, why do we care about like +1? We also can put here -1, right? Because it's also automorphism of this of Z2. It changes the orientation, but well, why not? You can also do it. Then this equivalence is called improper equivalence. And the equivalence with determinant +1 called proper equivalence. So proper equivalence is better in several aspects. So it's just technically it's better. But in a sense, it's just the same up to the transformations that when you change x, y, for example, to x minus y. Right? So for some forms, so for example, for these forms, for sum of two squares, it's the same. But if you have here b, which is not 0, then it means that this is a ABC goes to a minus BC, right? So that's improper equivalence, and we don't consider it. So it's not that good as proper. Okay, so we stick to determinant +1. Okay, good. Then the determinant of a quadratic form is defined as b squared minus 4ac. And it's easy to check that it's preserved by the above equivalence. So it's not obvious, you just apply it and you see that indeed it's true. And then the number which we care about is h of d. That's the number of equivalence classes of forms with coprime coefficients and discriminant d. Okay, so it's kind of the basic question of classification. And well, the formula above, here it gives you this value of this number as a certain sum of well, fractions. Okay, now why it's still actual? It seems to be a very basic question, but there is still open problem. So prove that there are infinitely many positive discriminants such that the class number is 1, such that h of d is 1. Well, and still it's open. So for discriminants less than 0, it's not very difficult to prove that h of d well, is finite. And then you also can prove that indeed for every like number, there are only a finite number of d such that h of d is this number. And you can even classify some of such numbers. But for positive d, it's still an open question. So even though there are many formulas for h of d, I will present them like at the end of the talk, still usually they involve both positive and negative terms. So you have a formula, but you don't know about the signs of terms or some other constants which are difficult to estimate. So maybe you present your h of d as like a plus b, but a plus b by themselves also you cannot estimate them. So in this sense, the formula above is good because you see, so here you have only positive terms. Well, actually, we will see that the terms will be positive here. And that's good. So it means that, well, maybe they're small, but at least they're positive. So it means that you can compute it. Like if you have a computer and you run it, and then you like easily find good estimates. Okay. Now let's see how these equivalence classes of forms are related to the topographs. So let me draw the topograph. So here I have this, and this. And you remember that every region corresponds to a vector. So let's say here we have E1, which is 1, 0. Here we have E2, which is 0, 1. Then here we have 1, 1. Here we have the difference, say 1 minus 1. And then we compute the values of the quadratic form on these vectors. So, for example, we have form ax squared plus bxy plus cy squared. That's our f. Okay, then what is the value here? Here it's just a. Okay, so here it's just b. And here just a plus b plus c. Okay, now what is the value here on this edge? Well, so not b, here it's c, right? Yeah, because when you put 0, 1, only the last term survives. Okay, so as you remember, whenever we have a topograph and we have such a piece of it, so here we have, let's say, R, S, and T, then they form a arithmetic progression. And so here on the edge, you write S minus R plus T.
Isn't it just the opposite that A and C should be switched?
Ah, right.
Okay, just I thought I was confused.
Yeah, it's sure. So here it's A, here it's C. Okay, good. And anyway, we just write B here, right? Because here we should write A plus B plus C. Well, minus A minus C, right? So according to this rule on the right. So actually it means that when you have a quadratic form, when you just look at the topograph, that's exactly two values near an edge. Here. Okay, now let's look what happens on the next edge, right? So here we have this one, and so here we have the sum of this. So okay, so here we have C, and then we have A plus B plus C, and so here we have X. They must form an arithmetic progression. And so what is X? I think X is just 2A plus B plus C. Right?
2A plus B plus C, yes.
2A. Okay, so let me write it here. 2A plus B plus C. Right, and they form the arithmetic progression. Good. Or maybe something is wrong.
4A plus 2B plus C.
So,
Right.
right. So let's compute it. Okay, so it should be, well, let's do it. Like X plus C should be equal twice to A plus B plus C, right? So it's 4A plus 2B plus C. Good. Because we have this rule that, well, so here if we have R, S, T, U, then U, R plus T and S must form arithmetic progression. Okay, so, and what is the value on the edge here? The value on the edge must be 2A plus B, I think. Right, because it's the value like A plus B plus C minus C. Right, 2A plus B. Okay, good. Now let's look at this part here. So again, so here we have the value A. On the edge, we have 2A plus B, and here we have A plus B plus C. And note that that's exactly what happens with the quadratic form when we change coordinates. So how we should do that? I think we had ax squared plus bxy plus cy squared, and now we have ax squared plus bx x plus y plus cx plus y squared. No, the opposite, right? Right. So it's better to change x. So here we have a x plus y squared. So I just okay. So let's do it with this one. Then we will see. So it's a x plus y squared plus b x plus y times y plus cy squared. Right. So if we develop the parentheses, it will be a x squared plus xy times 2a plus b, right? And plus y squared times a plus b plus c. Oh, okay, good. So that's exactly these three numbers which we have here. So it's a plus b plus c. And on the edge, we have 2a plus b. 2a plus b here, right? So it means that if you just move on the topograph along one edge, it means that the following change of coordinates. X goes to x plus y goes to y, right? So here we turn left. If we turn right, so if we go here, so this corresponds to the change of coordinates. X goes to x, y goes to x plus y. So it means that, well, we have these two generators, and these two generators, they generate the whole SL to Z, right? So it's enough to apply just the matrix 1, 1, 0, 1, and the matrix 1, 0, 1, 1. So that they generate the whole SL to Z. So it means that if we start with the form A, B, C, so here, then what we see on this topograph, it's all the forms which are equivalent to the form ABC. Okay, so it means that what I put here, that the equivalence classes of forms, they're in bijection with topographs. So it's just the same. So if you start with ABC and you write here A, B, and C, and then you just generate the whole topograph according to our rules, then all edges, they represent all the forms which are equivalent to the given form. Okay. And now let's see what we sum. What are the terms of the sum? The terms here is 1 divided by a plus b plus c, c. Look at the topograph. So here, that's exactly here. It was a. Okay. Let me draw a new topograph somewhere here. It was a here, c here, a plus b plus c here. Okay, b was on the edge, but it doesn't matter. So it means that in the sum above, so here we just take a topograph. What are these numbers? Like a bigger than 0, b for c is equal to d. So it means that we take all the possible quadratic forms of discriminant d, and we take a sum of such things. Actually, now you can split it into sums over all topographs. So it will be just the sum over the all topographs here times the sum over this a plus b plus c times c over one topograph. And then,
You mean over the vertex,
yep,
over the vertices of the topograph, right?
yes, over the vertices, and here we take just a, c, a plus c. Just for each vertex, take the product of the labels on the adjacent regions. Now, the mystery, as we have seen last time, is that actually this term is constant, does not depend on topograph, does not depend on topograph. So it means that actually, so the whole sum here, it counts just the number of topographs times a constant. So it counts the number of equivalence classes times the constant. Okay, what is the constant? Well, the constant is here. Well, the inverse of this constant. That means that we can just deduce this constant from this formula. So here, usually omega d is 2, right? So it means that this thing is usually just 6 pi divided by d power 3/3. So it depends on d, and that's not okay, because if you just multiply all the coefficients of your form by 2, for example, then all the terms are, well, divided by d with this power. But it's a constant. It's very interesting. Now, how it's all connected to the formula above here? Well, because that's exactly what happens for the form x squared plus y squared. Right? If your form is just the square of the length of the vector, then when you apply it to every vertex of the topograph, so here you have a vector x, vector y, vector x plus y, then you just apply this form. So here a will be equal to x squared, c will be equal to y squared, and this is a plus b plus c. And so actually, so this thing here just computes what happens for one form. Well, so here summation is not exactly about the whole topograph, but it's about a part of the topograph. But in a sense, you just, with standard combinatorial rewriting, you will see it always like that, like that. And also, now I can explain what happens. Because what happens when you sum over all the topograph? Let me just open the empty page. So you remember that our formula is for all the pairs of vectors in the first quadrant. So you start with E1 and E2 and you generate everything. So it means that you start here with topograph here E1, E2, E1 plus E2, 2E1 plus E2, and so on. So just to take the right part of the whole topograph. And then, as you remember, when we take a sum of this, we basically obtain constant times this angle. Okay. And now how to compute all the possible pairs of vectors, how to compute all the possible bases. To compute all the possible bases, you start like in several directions. So you start with the vertex here. So here you have E1 minus E2, for example, like that. Well, like that. So you have a sum of 3 vectors is 0. So here you start with, let's say, E1 minus E2 here, this one. So basically, when you compute the sum of all these terms, you will have this angle plus this angle plus this angle times a constant which depends on d. And then it means that it doesn't matter from which basis you start. So you may start from the basis, like this, and this. And then you see, so all the forms with negative discriminant, let's say, they equivalent if you allow matrix, SL to R transformations. So basically, from this point of view, how to relate this sum here to any form, to the standard form, just apply a change of coordinates such that your form becomes standard, but the vectors on which you evaluate your form, well, now they're different. So that's just some lattice, which is not Z2, but another lattice. But as we remember, so if you just take other lattice, then again, all these sums, they just can be expressed via angles. And the total angle is 2 pi. So that's exactly, this 6 pi here. And then since in the computations we had certain areas, well, we have divided by the areas, which will be D in this case, and so on. So this formula actually is just technical consequence of what we did last time. So using geometric arguments. So we just look at topographs and this sums becomes natural. Well, any questions here? Let's stop for a second.
So what happens with positive discriminant? If you is there anything similar?
Yeah. But you see, so it's just technically it's a bit more complicated because how can we get any negative discriminant? Let's remember this last talk. So, for example, so when we just change our form from A, well, the sum of squares, like we consider form x squared plus y squared, but then we want to consider form x squared plus 2y squared. So what we do, we just change the basis, right? And then again, so the form is equivalent over SL to R to the standard form. Then what we did, so we said, well, we have some formulas, but then in these formulas we can plug imaginary t. So how to get to another form? Well, so here, when you plug just y equals y prime, then you pass to x squared minus y squared. So in a sense, instead of looking for the angle between like 1, 0 and 0, 1, so what is the angle? Angle is some arctan of something, like of the angle. Now you look for the angle between 0, 1 and 0 and 1, 0 and 0 I. And still you can use the same arctan, but now it's like the complex argument. So that's how you pass to the forms with positive D. You should look at look at the convergence, because if you just do it like in the wrong way, the sum will diverge. So you should just take convergent parts. But otherwise, it's just well, the same as we did here to get this form. That's no in my language. In the articles which I mentioned in the beginning, they also do it, but like with different tools. Maybe let me return here to the beginning. So here in Hurwitz's paper, he has only discriminant less than 0. So the motivation of Duke, Imamoglu, and Toth was to extend it to d bigger than 0. So basically the same methods works, but you need some adjustment. I mean, they're technically more involved, and maybe the Hurwitz didn't know such things. And for Sullivan, the idea was to extend it to all possible d, because, for example, here there are problems when d is a square, right? So I think that here when you write d is like n square, then there are some problems. But here it's just for any d, and also related to topographs. So the formulas are rewritten in terms of topographs. Such a way they become more simple. So this paper is without topographs. They just have summations of something like of fractions, which depend on A, B, and C. Other questions? Okay, now let's go to the Sullivan's results. Let me explain. something. So what happens for positive discriminant? Okay, now let Q be a form, a binary quadratic form, ABC, with discriminant D, and say D is bigger than 0. And okay, when you have a quadratic form, it's natural to consider quadratic equation, right? You just write a xy squared plus bxy plus c equals to 0. It has two roots. So if d is negative, then two roots are complex numbers, conjugate, and it's very helpful to consider, them. And if d is positive, well, still you can consider the roots. The roots are real numbers, denoted by zq. Okay. Another important thing is the fundamental unit. It's epsilon z. It's defined in the following way. So let's consider the Pell's equation t minus d u squared is 4. Take the smallest positive solution. So when both t and u are positive, and, well, divide by 2. Okay, now there is a formula for the class number, which is contained in Sullivan paper. And it should be seen as a generalization of Hurwitz's formula for positive d. So here just take the power of the fundamental unit, power h of d, and this is equal to the product of these roots for all the forms. For which forms? For the forms such that a plus b plus c is less than 0, a and c are positive, and b squared minus 4ac is d in the ecoprime. Actually, one can show that there's only finite number of forms like that. So you consider all of them, take their roots, take their product, then take the logarithm with respect to epsilon z, and that's your class number. Well, let's see. So what is here? So here, all these forms q1, qn are so-called z star reduced forms. So when you speak about forms with negative discriminant, in every equivalence class, there is only one so-called reduced form. So that's the form such that, okay, let me write here. So if d is less than 0, then reduced means that b is less than a, well, less than c. Well, maybe with, sometimes you have equalities. But for the case when d is positive, you cannot find just one reduced form in every equivalence class. So there's different definitions of reduced forms and so on. So there are so-called Tagir reduced forms, and these are Tagir star reduced forms. But what it means is just these conditions that we have here in the product. And these forms are easily seen on topograph. So you remember, so we have a topograph for this form with positive d. So here d is positive. And if d is positive, that your form is something like, x squared minus dy squared, for example. So it assumes both positive and negative values, and you can draw the river. The river, that's a path in the topograph which divides positive values from the negative values. And then in this case, you can show that what you see on top, like let's say on the positive part, that's a periodic. So it's like 59, then something, 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 59. It's the same here. So you can take this, and that's general phenomena. It's not very difficult to prove. Basically, it just, if you remember how to solve the Pell's equation, basically it corresponds to continued fraction of the square root of d. And it's also periodic. So that's equivalent to the fact that the continued fraction for a quadratic rationality is periodic. Because, well, in a sense, that's exactly what you do. And so there is a river, it's periodic, and you can look at the forms which correspond to the edges just above the river. And actually, that's exactly the reduced forms. So you see, so why topographs is good? Because like classically, you have to define reduced forms with such conditions like that, and then you show that in every equivalence class of forms, there is at least one reduced form, but maybe there are many of them, and you do something with them. So it's complicated. But now you say that, well, if you have a quadratic form with positive discriminant, then let's look at the river on the topograph. It's periodic. And the reduced forms are just the forms which live near the river. So I think it's much nicer than like any algebraic definitions. Okay, so what we should do, we should just take the product of the roots of these like quadratic forms corresponding to these edges. And as you remember, so when you look again for these telescopic formulas, the sum of like fractions is approximately the angle between the generating vectors. What is the angle? Angle is arctangents. But what is arctangents for the case of complex argument? That's more or less logarithm. So basically what we say here is that when we look at the vectors here, like E1, E2, E3, E4, and so on, En, and we just look at the angle which is in between of them, but since d is positive, it should be the logarithm of this angle. So it means that this h of d is the sum of this minus this logarithms of minus b plus square root of d to a plus something. So that's the same idea. So you present this sums over topographs. So the total sum of all topographs splits into equal terms. And so the total sum is proportional to h of d. But now, you should consider only these parts of the topograph, because otherwise the sum will be infinite, because the topograph is periodic. So you just take a part of it, but then you can also compute the like sum over this part of the topograph, just on one branch here. And so this thing corresponds to the logarithm of this root. Okay, I just tried to explain the ideas. Now let's look at other formulas which are known, which are used before. So the classical number is as follows. So if you have a fundamental discriminant, so that's d which is 1 mod 4, or like 4 times something which is 2 or 3 mod 4. And let this q of square root of d will be corresponding imaginary quadratic field. Let's define the Kronecker symbol. That's a generalization of Legendre symbol. But so in Legendre symbol, you say that d and n are prime. But so here we just allow them to be any integers. And well, there are some axioms how to define it. And then it defines a real primitive quadratic Dirichlet character modulo d. So it depends on n, just n mod d. And you may, it's multiplicative. That's basically one of the axioms. We may form L function. So the famous Dirichlet L function, just compute this xi d of n divided by n power s. Then it can be extended to s equals to 1. So this summation. And then the classical formula, that's actually how Dirichlet studied the class number formula, h of d. So you have this 2, 4, 6 here. And this omega d is actually just the number of units in this field. So when d is minus 4, then you have 4 units, 1, I, minus 1, and minus I. When d is minus 3, then you have 6 units. 1, 2, 3, 4, 5, 6. And if d is less than minus 4, then you have just 2 units, 1 and minus 1. And so here you have square root of d, 2 pi, and then you have this L1 of x of d. But now you see, so this formula is good. And it's miraculous, because h of d is integer number, but here on the right you have a lot of strange stuff. You have this number of units, okay, which is integer. but then you also multiply by square root of d, divide by 2 pi, and then you have this mysterious number L1 sheet d, which is just infinite series. Well, then you can also rewrite with a finite sum. So again, you have some constant, and here you have this chi of d of m multiplied by m. Here the sum is finite, but so as you remember, this Kronecker symbol, so it may be like 1, -1, or 0. So it means that this sum is good, but the terms, they have different signs. So some of them are positive, some of them are negative. Well, no idea how to estimate it. So as I said, well, it's very difficult to use this formula. Okay, that's the Dirichlet formula for the negative discriminant. Okay, what is the analog for positive discriminant? Again, also it's all very well known. I think it's like 18th century, well, 19th century. So here, if discriminant is positive, then we have a similar formula again. So that's h of d. It's proportional to the value of L function at 1 to the square root of d. But here you divide by the logarithm of the fundamental unit. So you remember, so this epsilon d, it corresponds to the minimal positive solution of Pell's equation. And again, here, so how to estimate it? Well, maybe you somehow estimate that L1 of chi of d is small. Or maybe, I mean, so you want to prove that h of d like is 1, not very frequently or very frequently. Maybe you can estimate the L function, but then you have a problem with epsilon d, right? Because that's the minimal solution of the Pell's equation. Maybe it's small, maybe it's big. Again, just no idea. So the conjecture is that infinitely often this thing is 1. So it means that infinitely often this minimal solution of the Pell's equation is proportional to this L function, the value at 1. Then, well, you can rewrite this formula in many ways. So for example, you can rewrite this one L1 of chi d as this expression also. Right? So you have this thing, which again may be positive, maybe negative. Here you have logarithm of positive number, but again, maybe it's positive, maybe it's negative. Or you can write that the power of epsilon d, the power, well, in the class number, is just the product of signs. But again, so here you have this minus chi d of m, which sometimes positive, sometimes negative, so it's very difficult to control it. And so the last formula, it reminds you, this formula of Cormac here. And maybe this formula is better, right? So because there you have some signs and the product, but here you have product of, well, quadratic ratio analysis. Maybe in some sense it's better. Maybe it's easy to compute. I don't know. Okay, that's all for today. Thank you for your attention.
Thank you. Well, questions? Well, a comment from my side. Today, I finally understood what's going on. Like you, why it's interesting, for example.
Okay.
Yeah. No, super cool. Thank you.
Yeah, I like very much this connection to topographs and to quadratic forms. So somehow you start with very simple geometric object, you just multiply the lengths of vectors, but then somehow it's related to like to everything.
Okay.
So next time I
Yes.
will talk about the relation to string theory, because in string theory they also have such formulas. I will not be able to explain the connection to gravity and to other stuff, but well, at least I show how they treat these formulas and how they define them
Uh,
and so on.
there is a question in the audience, but he will not hear unless I can repeat the question. I mean, to change just a very general question, if there is some picture involving real services, where is this? So algebraic extensions
So the picture,
there is
oh,
parametrically various real surfaces, and I guess orbits work is all related to this. Did you hear the question?
well, partially.
So the question is whether there is some way to see Riemann surfaces in all that, since Hurwitz is generally well known for his works on
I think it's a
uh,
different Hurwitz. That's another.
it's different.
Yeah, I think it's different Hurwitz. Another one. So this Hurwitz is about number theory, and that Hurwitz that's about like coverings and all this stuff. Well, I may be wrong, but I think it's different Hurwitz. Well,
Actually, I was going to make sure it's same Hurwitz.
I think that
Like,
Hurwitz, that's Riemann surface Hurwitz, is from 19th century, and this Hurwitz is from 20th century.
ah,
So this Hurwitz died about 30s, like 80s, 30s.
okay, then it's different Hurwitz. Yes.
Well, I'm not sure, but well,
Well, I don't know. So, but yeah, a home
yeah, but
turf.
in a
In,
sense, that's related to Riemann surfaces. Actually, I don't know how, but I think that's related, at least if you study, say, geodesics on a torus. So if you have punctured torus, you can also generate all this fundamental group by this like SL2Z transformations. And then you have a topograph, and you may write different things. For example, you can write the length of geodesics on it.
yeah, and field extensions are related to Riemann surfaces. That's the comment from the audience. So,
Yeah, but so here
uh,
it's quadratic fields.
yeah.
So
Well, and since you spoke about string theory is like ultimately about Riemann surfaces. So there is
yeah,
something.
but this corresponds to genus one string theory. So yeah, that's all about genus one surfaces, if you wish. That's connected to Markov triples also, because the tree to generate Markov triples, it's like just the same tree. And Markov triples can be thought of like lengths of geodesics on a punctured torus. So
Right.
it's all about torus in a sense. And then next time we will see that all these functions that they actually PSL to Z invariant. And since they're PSL to Z invariant, they're just modular functions. So in a sense, we just study, well, modular functions which are not holomorphic. Okay, not holomorphic modular functions. Maybe there are extensions for higher genus, but I don't know.
Mhm. All right. Yeah. Thanks a lot. Um, so we stop recording, right?
Yes, I stop recording.